At last, let me wrap up the topic of tournaments with one little curiosity. So this is an application of tournaments to the Vandermonde determinant. So this is not a very important application. It's a bit of a luxury because there are many ways to prove the Vandermonde determinant. Most of them are easier. And I will not even go through the proof in detail. I will just sketch the main ideas. But it's a long proof, but it takes you through some nice places. So you can find, so this will be a sketch, and you can find details in the lecture, in the notes from spring 2017, lecture 8. So recall the Vandermonde determinant from linear algebra. I mean, of course, there is no guarantee that you actually hear about it in linear algebra, but I guess it belongs there. So this is a determinant identity. It says the following. Let x1 up to xn be any n numbers or elements of commutative ring. Consider the n by n matrix V. So V is going to have n rows and n columns. The top row is all ones. The next row is the variables, so the x's. The next row is the squares of the x's. And so on. Basically, every row, you increase the exponent by 1. This was x1 to the 0, this is x1 to the 1, this is x1 square, the next one is x1 cube, and so on. It goes all the way up to x1 to the minus 1. And similarly in all the other columns. Formally speaking, you can also rewrite this as this here. The entry in row I and column j is xj to the I minus 1. This is called the Vandermonde matrix. And its determinant, the claim is that this is the product of xi minus xj over all I less than j. So as I said, there are many simple proofs of this just by algebra alone. Induction on n, you can do, there is an LU decomposition. There are various ways to do it. But here is a combinatorial one using tournaments. First of all, what does any of this have to do with tournaments? So how do that V and this product relate to tournaments? Let me first explain the connection for the product. That V is a bit harder. So as a warm-up, let's compute the following product. y12 plus y21, y13 plus y32, sorry, y13 plus y31. y23 plus y32. So basically you have several independent variables, yij, where ij runs over the pairs of integers. And you want to expand this. Well, you expand this in the usual way. You pick one addend from this, one addend from this, one addend from this, plus one addend from this, one addend from this, one addend, and so on. You basically expand it. You multiply together all possible combinations. It's an exercise in speed typing because you're going to get 8 terms. It's not that much fun. These are just 4 of them, and then there's going to be 4 more. For the 4 more, all you have to do is replace the first factor y12 by y21, so that's faster. Okay, but what do you see here? You see here all possible tournaments on the vertex set 1 to 3. There is a tournament with arcs 1, 2, 1, 3, 2, 3. There is a tournament with arcs 1, 2, 1, 3, 3, 2, and so on. And here are they all conveniently shown. The color coding is an arc from a smaller vertex to a larger vertex is blue. An arc from a larger vertex to a smaller vertex is red. So 8 possibilities, because for each of the pairs, you have 2 ways to either either send an arc from the smaller to the larger, or send an arc from the larger or to the smaller. So either blue or red. And 2 times 2 times 2 is 8. Needless to say, this is the same logic that you get when you expand it here, because you have to choose from 1, 2, and 2, 1. Then you have to choose from 1, 3, and 3, 1. And then you have to choose from 2, 3, and 3, 2. So this long sum is really simply the sum over all tournaments with vertex set 1 up to 1, 2, 3. And then for each tournament, you multiply over all arcs Yij. So this generalizes, of course. It's not just about 3, it's about any n. So if you take the product of Yij plus Yji, you get the same sum, but the tournaments have no vertices 1 up to n. Now, setting Yij equals xj for I less than j, and minus xj. So let me just use a case formulation. So xj and minus xj, let's say greater or equal, doesn't matter. Those arcs never appear anyway. So if we substitute these values of Yij into this formula, what do we obtain? This Yij becomes xj. This Yji, because j is now bigger than I, this becomes minus xi. So you get xj minus xi. That's something that we have seen above here, except I've made a mistake. This was supposed to be xj minus xi. I would have gotten the sign wrong. Okay, and now you have to do this appropriately. You have to replace this Yij by this. So now this can be simplified a little bit. If you look at how often a single xj appears in this product, it appears as often as there are arcs with target j. So it's the same as saying that it appears with power with exponent out in degree of j. And so that's one thing. And how many minus signs appear? Well, I'm going to say number of red arcs of D. And by red, I mean arcs that go from a bigger number to from a bigger vertex to a smaller vertex. So those are the arcs I've painted red here. Okay, so one side of the Vandermonde determinant has a nice description in terms of tournaments. It's a big sum over all tournaments. What about the other side? What about that V? Well, a determinant of a matrix, as you know, is the sum of all permutations of the corresponding set, sign of the permutation times the product from of the corresponding entries. And this the corresponding entries will here be x sigma of j minus 1 to the j. Nope, x sigma j to the j minus 1. Or you could actually transpose the matrix that would make it a little bit nicer. That corresponds to having a j here and then a sigma j minus 1. So these things start looking the same. But of course, this sum has a huge number of addends. It has, for example, for n equals 3, it has 8 addends. Whereas this has n factorial addends. So for n equals 3, it has 6 addends. However, the sums nevertheless are equal. And why are they equal? Because in this sum, you have a lot of canceling addends. And once you're done canceling them all, you get these ones. Now, there is a lot of things to show here. So here is the first. Each addend of this sum is actually in the other sum as well. So I'm gonna call this the small sum, and I'm gonna call this the big sum. So I can just say each addend of the small sum is an addend of the big sum. Why is this the case? Basically, because for every permutation sigma, there is a certain tournament that gives you this exact value. Indeed, for each sigma in Sn, there is a certain tournament, which I call T sigma, that has this equals this. And it's a nice exercise to find this tournament. However, all the addends of the big sum that are not addends of the small sum cancel each other out. And this is trickier. So how do addends in the sum cancel each other out? You're looking for pairs of tournaments that have the same, for which this product will be the same, but these signs will be opposite. So this product being the same means that the integers are the same. So every vertex of one tournament and the corresponding vertex of the other have the same integrity. This is plausible because the number of possible integrity combinations is much less than the number of possible tournaments. You are expecting some repetitions there. For example, in this case, for n equals 3, the all red, sorry, no, not the all red. This tournament and this tournament have the same integrity sequence, 1, 1, 1. Basically, because this is a cycle that goes 1, 3, 2, and this is a cycle that goes 1, 2, 3. So these two tournaments are obtained from each other by reversing the flow on this cycle. And this is actually the idea in the general case. So the idea is to find a 3 cycle, basically a cycle of length 3, and to reverse all arcs of the 3 cycle. This reversal clearly preserves the integers, because when you reverse the order on a cycle, every vertex, it loses an incoming arc, but then it gains another. So the integrity doesn't change. And is easily seen to flip the sign. Basically, because when you reverse an arc, it goes from blue to red or from red to blue, but then you do this 3 times, so the sign flips 3 times, so it flips. Now, the challenge is to, first of all, make sure that all the missing addends, so all the appropriate addends really have 3 cycles to begin with. So what I mean by appropriate addends, I mean addends that appear in the big sum, but not in the small sum. We want to cancel those. We don't want to cancel the others. That they have 3 cycles. And furthermore, that the cancellation actually works out. Like you have to do this with some discipline. For example, if you have this 1 plus 1 plus 1 minus 1, in theory, every addend here cancels another. This one cancels this one. This one cancels this one. This one cancels this one. For every plus 1, there is a minus 1. For every minus 1, there is a plus 1. Shouldn't this be 0? Well, no, of course, because you're canceling the same thing twice. Once you've canceled those 2, this one is no longer available for canceling something else. So you need to make sure that this doesn't happen with your addends here. That basically you need to pair them up. The ones with a positive sign and the ones with a negative sign, you need to pair them up so that each one cancels its partner. They're not supposed to like share partners between each other. So we need perfect matching. This is a word that I will properly use in a few lectures, but not yet. But you understand what I mean. Between the positive and the negative addends to make the cancellation work. And this is a bit trickier because, of course, here it was easy. You just have two add-ons to cancel. And they have, each of them has a 3 cycle, you just revert it. But when you have more vertices, you might have some troubles deciding. You might have several 3 cycles. Which one do you reverse? And once maybe you take the smallest one, whatever this means, but then you've reversed it and suddenly there is a smaller one around. Do you reverse that one next? What do you do? So it's one thing to explain that in theory they like every plus addend has a minus addend. It's another thing to actually find a matching that cancels them out. So there are several ways to respond to this problem. And the one I'm doing in the notes, this is going back to Ira Gessel. The whole proof is actually due to Ira Gessel in the, I think, in the 80s or the 70s. What he does is you don't cancel them directly, but you prove that there are equally many pluses and minuses by arguing that if you fix the number of 3 cycles, basically for every plus addend, there are, if you look at the tournaments with exactly k many 3 cycles, so if you fix a k greater 0 and consider only the tournaments with exactly k many 3 cycles, then each such tournament, so each such positive tournament can be cancelled against k negative tournaments. And those negative tournaments also have k many 3 cycles. So you don't actually decide which 3 cycle you want to reverse. You just do everything. You just do all of them. You do each of them at once, so you get k different partners basically. But those partners themselves have k many 3 cycles. This isn't completely obvious. So you have to check that reversing the arcs of a 3 cycle does not change the number of all 3 cycles. And that's a nice little lemma that you might enjoy proving. But once you know that, you get some kind of k to k matching. So instead of a perfect matching where you just have everybody dance with a partner, you have this kind of twisted everybody dances with, it's like everybody has k hands and holds a different partner on each of them. But the thing is, this might not be a perfect matching, but this does what you need. This shows that the number of positive tournaments, by positive, of course, I mean that the sign is positive, with exactly k many 3 cycles equals the number of negative tournaments with exactly k many 3 cycles. And so all the tournaments that have k many 3 cycles end up canceling out from the big sum. And the tournaments that remain are exactly those in the small sum. Once again, this needs to be proved. Everything here needs to be proved. But the idea, even from a bird's eye view, I think there are some very nice ideas here. The whole structure of the cancellation process, this whole k to k matching, and generally the thought that if you're looking at a determinant formula, or generally at an equality between polynomials, it doesn't hurt to really multiply something like this out and look at the result combinatorially like we did here, interpreting the product as a sum over tournaments, for example. It won't always be tournaments, but it will be some combinatorial structure. And then you work with this combinatorial structure combinatorially. Basically, combinatorics can help algebra out in many situations. And quite often, the result is not actually as easy as van der Mon's determinant, because this is, of course, overkill. But in some cases, in many cases, what you get is not something you could get for cheaper. All right, so much for tournaments. And now, so next time we'll be talking about independent sets and also about colorings.